In today's video, we're going to be comparing means of two different groups. This time we'll be using confidence intervals. And this is just an extension from our previous video of comparing two means with hypothesis testing. So using our paper towel example from the previous video on hypothesis testing, we're going to calculate a 90% confidence interval using SPSS and doing it manually. And if you want to read the objectives, you can go ahead and pause the video at this point. But let's go ahead and review the logic behind the t-test once again. And if you remember, we talked about this, in most test statistics are like a signal to noise ratio. So you have your signal, which is the effect of your model, divided by the error of your model, or in other words, the variance explained by the model divided by the variance that can't be explained by the model. And here, in comparing two means, the model we fit is the difference between the two group means. And the estimate of the error we use is the standard error of the differences between the two means. So let's take a look at a confidence interval. And if we're looking here at our basic confidence interval calculation, it is that we are taking a point estimate plus and minus the margin of error to get our upper and lower limits respectively. And so that creates a point estimate of, the confidence interval that we use in order to estimate some population parameter. And in this case, we're going to be estimating the population mean difference. Taking now the basic confidence interval calculation and converting it for use for our independent samples t-test confidence interval calculation, our point estimate becomes the x bar sub 1 minus x bar sub 2, or the mean of the first group minus the mean of the second group. And our margin of error is the t critical value times the standard error. And you might recognize this standard error as the denominator from our independent samples t-test example for the actual t-test calculation. But be assured that we're talking about the t critical value here and not the t-test value. So let's get right to our example. Remember, we used a paper towel example from doing our independent samples t-test. And so here's the scenario. The personnel in a consumer testing laboratory are evaluating the absorbency of paper towels. They wish to compare a set of store brand paper towels to a similar group of name brand ones. For each brand, they dip a ply of the paper into a tub of fluid, allow the paper to drain back into the vat for 2 minutes, and then evaluate the amount of liquid the paper has taken up from the vat. A random sample of 9 store brand paper towels absorb the following amount of liquid in milliliters, and that's this group of numbers here. And then an independent random sample of 12 name brand paper towels absorb the following amounts of liquid in milliliters, and that's right here. And our task is to calculate a 95%, oops, that's mistaken. Okay, that's better. A 90% confidence interval estimate of the difference in the two population means. Why did I change it from 95 to 90% confidence interval? Well, you'll see on the next slide when we use the same information or some of the information from our independent samples t-test to populate our confidence interval calculation. So if you remember, mu sub 1 was equal to our store brand paper towels, and mu sub 2 is equal to our brand name paper towels, and we'll continue with that naming convention. So using the formula from the previous slide, our confidence interval formula for the independent samples t-test, and the information that we have on our scenario, we can move on and calculate the confidence interval. Now this is a pretty busy slide, but we'll clean it up in the next slide. But if you look in the faded background here, this is the same information that we had from our previous example of doing the independent samples t-test. And what we're doing is taking our confidence interval formula for the independent samples t-test right here and populating it with the data that are already on this slide. And we do have to do a minor calculation or two. So the x bar sub 1 and the x bar sub 2 can be found in our descriptive statistics area from our previous example. And so we have our mean of 6.44 for our x bar sub 1 and our 9.417 for our x bar sub 2. When we subtract x bar sub 1 minus x bar sub 2, we get negative 2.977. To find our t-critical value, we already had that information from when we had to develop our decision criteria or our decision rule for our independent samples t-test, and the t-critical value is 1.812. But as a reminder, we can find our t-critical value in Excel using the t.inv.2t, because it is a two-tailed t-critical value that we're looking for, and in the Office 2010 or later. And if you're using an earlier version, it's TINV as our Excel function. So we have our x bar sub 1 minus x bar sub 2. We have our t-critical value. Now we have to find our standard error. If you remember in our t-test statistic from the independent samples t-tests, you could see it vaguely in the background here, where we have x bar sub 1 plus x bar sub 2 divided by our standard error right here. Well, we can take our standard error and extract it from our t-test by using some basic algebra. So if we have in our denominator the standard error, but we want to solve for the standard error, and we have our t-test value right here, well, we can essentially swap those two, and we can figure out what our standard error is based on the calculation. So if we have our numerator from our t-test, same numerator as before, and then we divide it now by our t-test score, we calculate out our 6.44 minus 9.417 and divide it by negative 2.478, which is our t-test score. We can solve for our standard error, which turns out to be 1.201. And as I said at the beginning of this slide, it's a pretty busy slide, but we'll go on to the next slide where we'll see that it's cleaned up a little bit, but we have the same information. And this is just a quick way that you can calculate out the information if you already have the hypothesis test that you've calculated, the independent samples t-test or hypothesis test. If you don't already have this information, you'll be able to gain it from the SPSS output, but also you can go back to the independent samples t-test hypothesis test slides and video, and you can extract the information from there, or you can just extract it from the slides that we have right here. If you remember from our other video, because our book doesn't have values for 0.10 significance levels, you have to go to Appendix A.2 to find the one-tailed value of the 0.05 level of significance with 10 degrees of freedom, and you get 1.81 in order to actually calculate the t-critical value for a 0.10 significance level with 10 degrees of freedom. That's a two-tailed test. But don't get too caught up with that. It's just a lot easier to go with Excel, and it's also a little more, it's quite a bit more precise also. So let's clean this up a little bit. So again, here we have our formula for the independent samples t-test confidence interval. And our basic model is that we have a point estimate plus the margin of error. And if you remember back a few weeks ago, the margin of error is actually just the t-critical value times the standard error. If we populate it with the values that we found on the previous page, again, the point estimate is negative 2.977, and that's the difference between our group 1, which is our store brand paper towels, the mean of our store brand paper towels, minus the mean of our brand name paper towels, and we get negative 2.977, plus and minus 1.812, which is our t-critical value that we found from Excel, times 1.201, which is our standard error. and we get 2.176. So our margin of error is 2.176. And if we look at our upper limit, we have negative 0. If we take our point estimate of negative 2.977 and add to it 2.176, we get negative 0.801 as our upper limit to our confidence interval. And if we take negative 2.977 and subtract 2.176 from it, we get our our lower limit, which is negative 5.153. And the interpretation is that with 90% confidence, we estimate that the mean difference liquid absorption capacity between store brand paper towels and name brand paper towels is between negative 0.801 and negative 5.153 milliliters of liquid. So let's take a look at this for just a second now. The range is between negative 0.801 and negative 5.153. What do you think it would mean if our confidence interval were to span 0 and say, let's just say for example, it was negative 0.801 and positive 5.153 milliliters? Think about that for just a second, and then we'll move on. So what that means is that if our confidence interval had spanned 0, that means that mu sub 1, or the mean of our store brand paper towel liquid absorption capacity, is approximately equal to our mu sub 2, which is the brand name paper towel liquid absorption capacity. In other words, if your confidence interval spans 0, the implication is that the two means are not statistically significantly different. So let's walk through how we would run the independent samples t-test in SPSS, which provides us both the result for a hypothesis testing and for a confidence interval at the same time. Very convenient, isn't it? The first thing we want to do is we would do with any example or any SPS exercise is to go ahead and define our variables. And in this case, we do our data entry a little bit differently for the independent samples t-test. So in our first variable position, and it doesn't have to be the first, but for convenience sake, we put it in the first variable position. We're calling it the name group, and that is just going to be the identifier between which is the towel, the store brand towel, and which is the brand name towel. So we put in group. It's numeric. The width doesn't really need to be very big, and the decimals are 0 because it's only going to be a choice of 2 integer level variables, because they're nominal variables and they're just labels. So when we put in our values now, what we have to do is we'll click on this on our SPSS. We'll click on the ellipsis 3 periods button, and it'll pop up here. And what we'll do is we'll type in value of 1, and then we'll call that store brand. Then we'll hit add for value. We'll put value 2 in. We'll hit brand name, and we'll hit add. Then we hit OK. Next, we can go ahead and enter our data set. And you'll notice that we put all of the data into one column. And then we use the group variable to distinguish from which group each observation is, or each data point is. And those will show up with either the actual value label that we entered in here, the value label, or it'll be a 0, or excuse me, a 1 or a 2, because we used 1 or 2 here. You could actually use 5 and 6 if you so desired on this, and it doesn't really matter as long as you, when you enter your information in your data point, that you choose the right label for it. And you'll also need to use the right label or the right variable, the right number, when you're working on it later in the actual analysis portion. So Here's how we go ahead and analyze it. We go to Analyze, Compare Means, Independent Samples t-test, which will bring you to here, and you put in your grouping variable right here. You put your test variable, which is our data column, in here, and that was called liquid absorbed. We define our groups. Now this, when you first put in your grouping variable, which we called group, in here, it'll be question mark, question mark. So you have to go in and define it before you can actually run the analysis, because SPSS wants to be sure which is group 1 and which is group 2. So you have to go ahead and specify that. Again, if you were doing 5 and 6, you could do 5 here and 6 here if that's what you really wanted to do. Just showing you that this is a way to do it. This could have been 0 and 1. If you were doing, say, a male-female comparison, frequently we use 0 to reference males and 1 to reference females, so this might be 0 and 1. Then when we go into our options. By default, the independent samples t-test in SPSS is going to do a 95% confidence interval. We're doing 90% because we want to compare our results to what we found in our manual analysis. So again, we hit continue, we hit continue again, and we hit OK, and then we can move on to our output. Now the first table, these are the two tables that you get as the output for the independent samples t-test in SPSS. If you do a bootstrap, which we chose not to, there was no bootstrap option in there that we selected, you'd get a third table if you did bootstrapping. But let's go through the different output that we have here. The first table is fairly straightforward and should be very familiar to you. So we have here in this column the different types or the different groups. So we have our store brand paper towels on the first row and our brand name paper towels on the second row. The N, it goes back to our number of observations, and we had, in our example, we had 3, 6, 9 store brand paper towels, and we had 12 brand name paper towels. So that's what we're seeing right here. This is the mean of our observations for the store brand paper towels and the standard deviation of our store brand paper towels. Now the difference here is the standard error, and this is somewhat new. We have seen standard error before, but this is the standard error of the mean, and that is the ratio of the standard deviation to the square root of the respective number of observations. So what does that mean? Well, if you take the standard deviation and divide it by the square root of the number of observations, so the square root the square root of 9 is 3. If we were to divide 3.321 divided by 3, we would get 1.107, and that is a measure of the variation. Now, same goes with brand name paper towels. N is 12. We had 12 observations. The mean is 9.42, and the standard deviation is 1.621. And the standard error of the mean is 0.468. Excuse me. Now we go on to the independent samples t-test, where we have a lot of the meat of our analysis, and this is going to be a little bit new to you. So let's go through each of the portions of this output. So now here we have two different rows. One is the equal variance is assumed, and the other is the equal variance is not assumed. Based on the scenario we chose to do the unequal population standard deviations, which is same as unequal variances, and we could have chosen equal variance is assumed, but we chose the equal variance is not assumed, so we're going to go through the second row is where we find our data. So before we do that though, let's go ahead and take a look at what this F-test and significance test is here, the Levene's test for equality of variances, and why is there just one of them? Well, the F-test, as its title explains, is the test for equality of variances. And the F-test, if you remember, we've discussed it before, is when we have one variance divided by another variance. And in this case, this is the variances of the two different means, or two different groups. So we have the store brand and the brand named, and we get our F-test. And the significance, that is the two-tailed p-value associated with the null hypothesis that the two groups have the same variance. So again, this is a test for equality of variances, and in that regard it's similar to when we do a t-test for variances. So in our example, the p-value is low, so the null must go. So the p-value is less than the alpha level, and generally speaking we choose a 0.05 level of significance. Technically you could choose another, but as a tradition we use 0.05 level of significance for the Levene's test for equality of variances. So in this case, the null hypothesis that the two variances are equal must go. So we can state that we believe that we predict or estimate that our variances are statistically significantly different, and then that just reinforces our choice to use the equal variances not assumed. If however we had a non-significant value, in other words our p-value is greater than 0.05 instead of equal to or less than 0.05, we could use the first row of data, but it wouldn't correspond with the calculation we did in the independent samples t-test hypothesis test, so we want to go ahead and continue with the lower row anyway. So let's move on to the t-test. In this example, or in this calculation, the independent samples t-test, the t-value is actually the ratio of the mean differences to the standard errors of the differences, and that goes way back to our, well, not way back, but it goes back to our calculation here that we did in the hypothesis test. It's grayed out on the top where you have x sub 1 or x bar sub 1 plus x bar sub 2, but you can still make it out, and if you have the slides you can actually uncover these and take a look at it, or just pull up the slides from the last session. So in this case, our t-value is negative 2.972, which was the mean differences, and you could calculate that just by subtracting 9.42 from the 6.44, and then divide it by 1.202, which you can use that calculation that we had on this page here, or you can cheat and grab it off of here. It's actually not cheating, it's there provided for you to use. The degrees of freedom goes back to our calculation here that's shaded out. Again, you can pull up the slides from the video from the other example when we did the independent samples t-test hypothesis test for the means using the same data set. So we came up with if you remember, we calculated it manually. I think we came up with 10.88 as our degrees of freedom. And then we have our significance. Again, this is two-tailed significance, and SPSS is kind enough to remind us of that. And we have a significance value, or a p-value, of 0.031 using the t-distribution. And what that p-value means is it's the probability of observing a t-value of equal or greater absolute value under the null hypothesis. If the p-value is less than our pre-specified alpha level, usually, again, 0.05%, we'll conclude that the difference is significantly different from 0. So again, if the p-value is low, the null must go. So for our example, the p-value is lower than 0.05, and that means, and that's for the difference between the store brand and the name brand paper towels liquid absorption capacity. So we conclude that the difference in means is statistically significantly different from 0. The mean difference is just that. The difference is between the two means. So it's 6.44 minus 9.42 gives us negative 2.972. The standard error of the difference, as we mentioned before, is it's the estimated standard deviation of the difference between the sample means, and it's an example of the measure of the variability of the data set. And so if we drew repeated samples of size 200, 300 or so, we would expect the standard deviation of the sample means to be close to the standard error, and that provides a measure of the variability of the sample mean. If you remember, the central limit theorem tells us that the sample means are approximately normally distributed when the sample size is 30 or greater. And one thing you'll note was we have two different values here. Well, for each of the different approaches, the equal variance is assumed or equal variance is not assumed, the standard error of the difference is calculated differently. And we went through and manually calculated the standard error of the difference in our null hypothesis test. So we can see that where we can calculate it out here using our algebra. And then we have our lower confidence interval and our upper confidence limit. Our lower level, our confidence interval, 90% confidence interval for the difference. We have the lower limit and then the upper limit of the confidence interval. You'll note these numbers are very similar to what we calculated when we did this manually. And again, SPSS takes it to many decimal places further than what we did in our manual calculation, which is some of the reason, or this is the reason why we have differences in our numbers here. And again, if you go back a couple of slides here, we have that note that if our confidence interval had span 0, what that means is that mu1 is approximately equal to mu2. In other words, the mean absorption capacity, liquid absorption capacity of the store brand paper towels is roughly equivalent to the mean absorption capacity of the brand name paper towels. So there's no statistically significant difference. And just for reference, I've got a couple of pages here of the explanation for each of these data points that SPSS provided for us. And I'll put them up there for just a moment. You can pause your video and copy them down, or if you have the slides, you don't need to pause the video and you don't need to watch. And that's all we have for this video. Hope you enjoyed it. See you for the next one.